Hi, and welcome to my talk. The topic of this session is how to use machine learning to automatically optimize Kubernetes application for cost efficiency and reliability. We will start by discussing the Kubernetes challenges for ensuring application performance and reliability, and then we'll review how Kubernetes manages container resources and the implication on performance, reliability, and cost. We will then discuss the approach we implemented at Akamas by providing a real-world example. Finally, we will conclude by sharing some takeaways. Before proceeding, please allow me to introduce myself. My name is Stefano Doni and my role is CTO at Akamas. Performance engineering has always been my topic of interest and passion. Let's start with a quick introduction to Kubernetes. I would like to start with an interesting story of how Kubernetes was born. Since its origin, Google has had immense challenges to scale their high-traffic applications like search and Gmail in the most efficient way possible. To do that, they had to invent a new system capable of managing billions of application containers running in large fleet of servers. It was called Borg, and it was really a top-secret project. In 2013, a couple of Google engineers wanted to bring the benefits of Borg to the wider world. The idea to build an open-source version of Borg was not well received at the beginning, but eventually they got the green light and so Kubernetes was born. Kubernetes has many benefits. One of the most important from a performance perspective is efficiency, which is the ability of Kubernetes to densely schedule containers into the underlying machines, which translates to lower infrastructure cost. At the same time, Kubernetes provides facilities to make sure applications are isolated from each other so that a runaway container won't impact your critical service performance. Speaking about cost, a recent survey found that Kubernetes spend is growing. This should not come as a surprise given the increased level of adoption. However, the report also found out that those cost increases are somewhat unexpected, in particular also reported by skilled organizations. So this begs several questions. Is this increase in cost only due to growing adoption, or are there some challenges in making sure Kubernetes environments are actually cost efficient? We will provide our answer to these questions shortly. Besides the increasing costs, there are more and more stories of how difficult it is to ensure performance and stability for Kubernetes applications. The Kubernetes Failure Stories is a website that was specifically created to share Kubernetes incident reports with the goal to learn how to prevent them. Many of those stories describe teams that are struggling with Kubernetes application and stability issues, such as unexpected CPU slowdown and even sudden container terminations. Engineers at Airbnb even got to the point of suggesting that Kubernetes may actually hurt the performance of the latency-sensitive applications. But why is it so difficult to manage application performance, stability, and efficiency on Kubernetes? The simple answer is that Kubernetes is a great platform to run containerized applications, but it requires applications to be carefully configured to ensure cost efficiency and high performance. Let's now get back to the fundamentals and see how Kubernetes resource management works to better understand the main parameters that impact Kubernetes application performance, stability, and cost efficiency. Let's go through 4 main key facts and their implications. The first important concept is resource request. When a developer defines a pod, she has the possibility to specify a resource request. Those are the amount of CPU and memory that the pod, or better a container within the pod, is guaranteed to get. Kubernetes will schedule the pod on a node where the requested resources are actually available. In the example, pod A requires 2 CPU and is scheduled on a 4 CPU node. When a new pod B of the same size is created, it can also be scheduled on the same node. This node now has all of the 4 CPUs requested. If a pod C is created, Kubernetes won't schedule it on this node, as its CPU capacity is full. This means that those numbers that a developer puts in a YAML file are used by Kubernetes to manage real cluster capacity. A quite surprising fact is that with Kubernetes there is no overcommitment on request. You cannot request more CPUs than those that are available in the cluster. This is very different from virtualization, where you could create many virtual machines with many more virtual CPUs than the real physical CPUs available. Another very important fact to notice is that resource requests are not equal to utilization. If a pod requests are much higher than the actual pod resource usage, you will end up with a cluster that can be full even though its CPU utilization is as low as 10%. So letting proper pod requests to be set is paramount to ensure Kubernetes cost efficiency. The second important concept is resource limits. Resource requests are the guaranteed resources that a container will get, but usage can be higher. Resource limits is the mechanism that allows you to define the maximum amount of resources that a container can use, like 2 CPUs or 1 gig of memory. All this is great, but what happens when resource usage hits the limit? Kubernetes treats CPU and memory resources differently here. When CPU usage approaches the limit, the containers get throttled. This means the CPU is artificially restricted, and this can result in application performance issues. Instead, when memory usage hits the limit, the container gets terminated. So there is no application slowdown due to paging or swapping like we had in traditional operating systems. With Kubernetes, your pod will simply disappear, and you may face serious application stability issues. The third fact is about an important and less known effect of CPU limits have on application performance. CPU limits work by throttling CPU performance. And you may think that this happens only when CPU usage hits the limit. Quite surprisingly, the reality is that CPU throttling starts when CPU usage is well below the limit. We researched this aspect in our labs and found out that CPU throttling can start when CPU usage is as low as 30% of the CPU limit. This is due to the particular way CPU limits are implemented at the Linux kernel level. So this aggressive throttling has huge impact on service performance. You can get sudden latency spikes that may breach your SLOs without any apparent reason, even at low CPU usage. Now, some people, including engineers at Buffers, tried to remove CPU limits. What they got was an impressive reduction of service latency. So is it a good idea to get rid of CPU limits? The answer is no. Remember, CPU limit exists for the purpose of ensuring that application can run fine and coexist without having performance interferences. So if CPU limits are removed, a single runaway application can completely disrupt the performance and the viability of your most critical services. This best practice is also recommended by Google itself. Properly setting your CPU requests and limits is critical to ensure your Kubernetes cluster remains stable and efficient over time. What we have just discussed about how Kubernetes manages container resources and their interesting implication explains why tuning Kubernetes is a tough job. However, as developers, performance engineers, or site reliability engineers, we know that a Kubernetes pod is just one piece in the overall picture. A Kubernetes cloud-native application is typically made of dozens of microservices, so the optimization challenge becomes even harder when considering the full picture. So the real question is, how can we set all of the microservice parameters, which include resource requests and limits, but may also include auto-scaling and application-level settings like JVM options, to ensure the overall application meets its performance and availability requirements and SLOs at the minimum cost? Achieving such a goal is a daunting task for performance engineers and SREs, given the complexity of tuning Kubernetes resources and the many moving parts that we have in modern applications. This is why we need a completely different approach. At Akamas, we have identified 4 key requirements that we believe are required to effectively solve this class of problems. First, the approach should allow a full-stack optimization, meaning that it has to be able to optimize several different technologies at the same time. For example, the optimization might focus on container parameters and runtime settings like JVM options at the same time. Second, the approach should allow a smart exploration of the space of potential configurations. If we consider all the possible values for all the possible parameters, we really have billions of configurations to try. So a brute force approach is simply not feasible and would not work for this kind of problem. To be effective, a solution needs to be identified in a reasonable time frame and at an acceptable cost. Third, the approach should allow us to align to a specific need, priority, and use case of interest by defining custom optimization goals. For example, in some cases, the user may want to reduce your service latency to provide the best possible performance at peak loads. For another user, the cost could be the key driver for the optimization while matching current service performance. And last but not least, the new approach should be fully automated to ensure a reliable process and the faster convergence to the optimal solution. At Akamas, we adopt a fully automated machine learning-based optimization that satisfies all of these requirements. In particular, we leverage specific machine learning techniques known as reinforcement learning, which are suited for smartly exploring huge combinatorial spaces of possible configuration in a short time. This figure shows the 5 phases of the automated process. The first step is to apply a configuration to the target of the optimization. The second step is to apply a workload to the target, so to assess the impact of the applied configuration. The third step is to collect KPIs related to the target system, that is, information, data, and metrics about the behavior of the system under the workload. The fourth step is the score of the configuration against the specific goal by leveraging the collected KPIs. The last step is where machine learning kicks in by taking the score of the tested configuration as input and by producing as output the most promising configuration to be tested in the next iteration of the same process. In a relatively short amount of time, the machine learning algorithms learn the dependency between the configuration and the system behavior, thus identifying the better and better configurations. This automated process enables a new performance tuning process where the user defines the optimization goals and constraints and then lets a machine learning-based optimization to automatically identify the optimal configuration. Let's see how this approach works in practice with a real-world example. In our optimization example, the target system is Google Online Boutique, a cloud-native application running on Kubernetes made of 10 microservices. This application features a modern software stack with services written in Golang, Node.js, Java, and Python, and it also includes a load generator based on Locust, which generates realistic traffic to test the application. This is the overall architecture. The parameters we are optimizing in this example are the CPU and memory limits of each microservice. These parameters are applied via the Kubernetes APIs. In order to assess the performance of the overall application with respect to the different size of the containers, we leverage the built-in Locust to inject the workload. We then leverage Prometheus and the Istio service mesh, respectively, to gather pod resource consumption metrics and to gather service level metrics. The whole optimization process is completely automated. So what is the goal of this optimization? In our example, we aim at increasing the efficiency of the online boutique application. This means to both increase the service throughput and to decrease the cloud cost. At the same time, we want our service to always meet its reliability targets, which are expressed as latency and error rates, SLOs. Therefore, our optimization goal is to maximize the ratio between the service throughput and the overall service cost. The service throughput here is measured by Istio at the front-end layer, where all user traffic is processed. The service cost is the cloud cost we will pay to run the application on the cloud, considering the CPU and memory resources allocated to each microservice. In this example, we use the pricing of AWS Fargate, which is a serverless Kubernetes offering by AWS, which, for example, charges $29 per month for each CPU requested and about $3 per month for each gigabyte of memory. Akamas also allows to set constraints to which configuration are acceptable. In this case, we state that configuration should have a max 90 percentile latency of 500 milliseconds and an error rate lower than 2%. That is it. At this point, the machine learning-based optimization can run automatically while we are relaxing or doing some other important stuff. So let's now see what are the results that we got. In this chart, each dot represents the cost efficiency of the application, which again is the service throughput divided by the cloud cost, as a result of a different configuration of microservices, CPU, and memory limits as chosen by the machine learning optimizer. So the result of our machine learning-based optimization approach is quite astonishing. A configuration improving the cost efficiency by 77% was automatically identified in about 20 hours of automated tuning. The baseline configuration, which corresponds to the initial sizing of the microservices, has a cost efficiency of 0.29 transactions per second per dollar per month. The best configuration for machine learning found by tuning microservices resources achieved 0.52 transactions per second per dollar per month. This chart also helps understanding how our machine learning-based optimization works by learning from each tested configuration and to quickly converge towards the optimal configuration. At this point, I guess you may want to know what is the best configuration look like. So let's inspect the best configuration by focusing on the 10 most impacting parameters. So it's interesting to notice how our machine learning-based optimization reduced the CPU limits for many microservices. This is clearly a winning move from a cost perspective. However, it also automatically learned that two particular microservices, the product catalog and the recommendation, were under provision. So thus, in this case, the machine learning increased both the assigned CPU and memory. All these changes at the microservice level were critical to achieve our optimization goals that we set on the higher level service, which is to maximize the throughput and lower cost, while still matching the SLOs that we had. Let's now see how the overall service performance changes when the best configuration is applied. The chart on the left shows how the baseline and the best configuration compare in terms of the overall service throughput. Interestingly, besides being much more cost efficient, the best configuration also managed to improve the throughput by 90%. On the right, we are comparing the service 90 percentile response time. In this case, the best configuration cut the latency peaks by 60% and made the service latency much more stable. Alright, it is time to conclude with our takeaways. Our first takeaway is that tuning application based on Kubernetes is a complex problem that is hard to solve with the traditional tuning approaches. The second takeaway is that we need a new approach to be able to effectively solve this class of problems. We have described the key requirements for this machine learning-based optimization that we refer to as autonomous performance optimization. Finally, we have demonstrated that this new approach works. We were able to automatically tune Kubernetes and microservices to maximize application transaction per second while also minimizing cost. Many thanks for your time. I really hope you enjoyed the talk. Please send us any comment and question by leveraging these contacts.
Thank you so much, Stefano. This is always
You're welcome.
a pleasure to see how you guys keep pushing the boundaries of how we can be more efficient, while also it appears cheaper. So that's kind of like a perfect hit there. Okay, let's see what questions we have so far. Alison, what is the first question? Resource limits. So I don't know about you, but most of the engineers I know, they're trying to max it out so that their service performs the fastest and also, more importantly, doesn't get killed. So I'm wondering, in your experience, what are the incentives and also the tools that they should use to do right sizing?
Yeah, that's a great question. So as regard the incentives, I guess this is the practice that I also see applied the most. And I guess that's the reason why we see this kind of rising cost, because as we have seen, these simple numbers that engineers put on the YAML files can actually drive the cost of the clusters, also considering auto-scaling clusters on the cloud, etc. So as regard so it's a good question. The incentives, probably performance. Typically, software engineers do not have great incentives, but they are more, in a way, driven to keep the service up and make sure latency is good, etc. So, of course, this becomes a cost issue for the more kind of the financial department, something like that. So, at the end of the day, it's important for the company to be able to drive down the cost while still maintaining reliability, of course. So, the most typical approach that I see, I think it's that also many times suggested also the best practice is just monitoring. So basically, I see lots of people leveraging APM tools or even open source tools like Prometheus and just monitor container metrics and try to, of course, avoiding impact of CPU throttling and something like that. Of course, these are very simple solution that requires lots and lots of work because especially with microservices, you have lots and lots of containers to look at. So it's not just like the monolith that you have just one single thing to look at. So you have lots of containers. It's tricky still because as we have seen, you have this kind of weird behaviors of spikes on response times, and you sometimes also, but with the APN tools, you are not well supported in understanding where is why is the sometimes latency going up, etc. So it's still tricky, I guess, for engineers. And then, of course, you have the other thing, which is application gets released often and often. So again, it's very hard, lots and lots of work that you have to do to, in a way, keep up with this process. So that's the reason why we believe it should be automated.
That's a good segue to our second question, which was really, okay, ML is obviously the way to go, especially in a fast-moving code base. But is ML ready to take into account all the complexities of the real world, like patterns in traffic that shift depending on seasonality, things like that? How do you do that?
Yeah, that's a good question because it's actually very hard to come up with a solution like this one. Actually, there are two ways to tackle this problem. One is to, in a way, work in kind of pre-prod environments where teams are actually simulating traffic spikes and reproducing the workload that they expect, for example, for an upcoming event like the Black Friday. So this is basically what teams are doing today. So they predict what will be the traffic for the peak, and then we do the performance tuning on the peak, which is usually the approach that works today. So the same can be done for with a machine learning based approach. You can simulate your traffic, and then you have the plus that this kind of process gets completely automated. The other approach will be actually to do that live in production. So we are working on that. It's actually very complex because, as you said, there are lots and lots of complexities. You have the traffic that is changing in the volumes. Traffic may change also in terms of the mix, or application gets released. So that's a challenge. Yes, but we are working on that, and we really think machine learning can also be used to solve this, in a way, holy grail kind of problem.
And kind of last question, and I want to see if there is a hope for us humans. Do you think that ML has surpassed the skilled performance engineers, or there's still hope for us?
That's a great question because actually I really think that I'm a performance engineer. Like I'm doing this kind of stuff like for for 16 years or so. So when we started applying this approach, I was myself really surprised at defining this, because we are finding very counterintuitive in a way kind of results that we as performance engineer would have never tried. Sometimes, for example, machine learning learns that it has to, for example, tune the Linux system in a different ways in order to make a database run faster than that is running on top. So it's also a matter of very high number of parameters that you may tune at the same time, also for different layers. So it can really find out some performance gems that are very, very hard to do with our human-based approach, because we usually still tune one thing at a time, but when you have 60 parameters, it's nearly impossible. And the other thing is that, nevertheless, this performance engineer or the SRE doesn't get, in a way, automated away, because he still has the important, in a way, task to define the optimization, to define the goal, to actually define the constraint, and to supervise the process. So it's not that we are, in a way, removing the human, but from the loop, but actually I see by you actually seeing also users of our tool, actually, that it gets much more interesting, because you can learn from the finding, you can define new optimization based on what we have learned. So it gets a lot more fun and exciting that that it is today, actually.
Okay, so in the end, we'll end up in a partnership, very likely, where there will always be the human intuition, but for brute force, 60 parameters, ML will always kind of lead the way. Right?
Yeah, definitely.
All right. Thank you so much, Stefano, for the great talk and the insightful answers.